In this video, we will talk about potential challenges of current limited operation of grid following or grid supporting voltage source converters on small signal stability of power systems. The power converters, especially the ones installed primarily to provide active power such as voltage source converters for battery energy storage system, have limited headroom available for reactive power support, which means a mode change for voltage source converters for a voltage control mode to current limit mode when the system is stressed. How does this impact dynamic Thevenin network impedance seen by the other components in the system? Although the transition to current limit mode may be seamless to the external circuit, the dynamics of the system has changed due to the change in control loop structure. The impact of this change can result in interaction with other voltage source converters or any other components in the system and may potentially result in instability. The current limit in voltage source converters and associated mode change is entirely different from the synchronous machine, which maintains voltage source behavior even at triggering of limiters such as overexcitation, underexcitation, or stator current limit. The paper first derives the desirable characteristics of the impedance of parallel connected components in a power system, which can avoid unwanted oscillations in the system. That the impedances of voltage source converter and the synchronous generator with and without the limiters are compared against each other and checked if they satisfy the desirable characteristics for a parallel connection. Finally, a case study is presented to verify the results drawn from the analysis. A simple power system circuit as shown where the stability of the device under test which is connected to the infinite voltage source via two series connected transmission lines are investigated. For this circuit, we could write the desired characteristics of parallel impedance shed shunt of test, which reduces the adverse interaction between the device under test and the network as low impedance magnitude, particularly at low frequency range with no negative real part at any frequency, low variability and no discrete jumps in impedance magnitude for any change in the operating point. What if the shunt element is a synchronous generator? From the derived impedance of synchronous generator, we can note that the controller influence is limited to below 10 Hz because the AVR has low bandwidth. The impedance magnitude remains below 1 per unit for low frequency range. Furthermore, the operating point has limited influence on the impedances. And finally, the excitation limiter activation increases the impedance in the low frequency range. However, the increase in magnitude is minimal. What if the shunt element is a grid supporting VSC? For the derived impedance of grid supporting VSC, we can note that the variability in the impedance for different operating points are high, except within the bandwidth of the voltage control loop, the impedance is higher than 1 per unit and shaped by current control. The phase of the dynamic impedance is higher than 90 degrees in the low frequency range, pointing towards the negative resistance characteristics. The activation of limiters can result in large discrete upward magnitude jumps in dynamic impedances. A simple test power system is simulated in Aerostat. The test power system consists of a parallel connected 70 MVA synchronous condenser and grid supporting voltage source converter. A 140 MVA grid following voltage source converter is the device under test. The response of the 140 MVA voltage source converter when one of the transmission line impedance is increased by 0.05 per unit is recorded for 3 test cases. The 3 test cases are the system with only parallel voltage source converter with no current limit, only parallel voltage source converter with reactive current limit, and both parallel voltage source converter with synchronous condenser and reactive current limit. In the parallel connected 70 MVA voltage source converter and the current limited mode, the system becomes unstable, whereas the response remains stable when a parallel connected synchronous condenser is present or when no current limit is triggered in parallel connected voltage source converter. The conclusions from the study are the impedances of the network dominated by power converters have high variability and is highly dependent on the operating point. Upward jump in Thevenin impedances when current is limited could potentially give rise to oscillations at very low frequency range. The synchronous machine's impedance remains low in low frequency range at all operating conditions and even when the excitation limiters are triggered. The proportion of synchronous condensers are recommended to be maintained in the network to avoid or limit adverse interactions by power converters.